Hello and welcome to another worked example for the classical mechanics course in 2023. Please read the problem. I will fix the typo while you read it, and then we can get started. Okay, while you read the problem, I also made a little drawing to get an idea of the geometry. Here is in green is the pendulum, length L, mass M. It's attached, its pivot point is attached to a circle, and it moves with velocity, angular velocity omega. So the motion is in this direction, and the angle formed by the position of the pivot and the horizontal is going to be omega times t, and this length is a. The angle between the pendulum and the vertical is theta, and other color. Of course, let's just use a different color. Gravity points down. Okay, now we hopefully have everything. Equations of motion. Well, the first thing you have to wonder is how many degrees of freedom does the system have? And the answer is maybe not so obvious, maybe it is. The answer is actually 1, theta, the angle. The motion is in the plane, so I only need to give the angle, the position of the mass m as coordinates x and y, but since the mass is attached to an oscillating pendulum, and we know as a function of time the position of the pivot of the pendulum, in fact, once I give theta, I can determine the coordinates x and y for the mass. And I'm going to show this to you in a second. First thing, I said, well, x is going to be equal to a times cosine of omega t. That's the position of the x of the pivot. So let me call it xp plus b times the sine of theta. And that I'm going to call x of the pendulum. Can't do that. So let me call it x sub m, the position relative to the pivot of the pendulum. And for y, well, I'm going to have the position of the pivot, a times sine of omega t, y is a p, minus, since y points up and the pendulum is down from the position of the pivot, minus b times, no, sorry, it's not b, it's L. Sorry about that. I was just following the alphabet. The coordinate is called L times the cosine of theta, which I can call y sub m. So that's the complete position of the pendulum. Then I can get the velocities. So this is position. Then I can get the velocities. So let me pause. I just jumped in because this problem is so fascinating. But what am I going to do? Well, I want to write the Lagrangian for the system. That will make it very easy for me to write the equations of motion. In order to write the Lagrangian, I need the kinetic energy and the potential energy. The kinetic energy is going to be given by 1/2 of the mass times the velocity squared. So I need an expression for the velocity. Easiest way to do it is to use Cartesian coordinates, find x of t and y of t, and then take derivatives of x and y, and find vx and vy, and that will give me an expression for the velocity square, and therefore for the kinetic energy. As for the potential energy, since gravity points down, all I need is y of my mass. Okay, then I found the position. Then I take the derivatives with respect to time, and I find the velocities. Derivative of the cosine is minus sine, so I get minus I omega sine of omega t. Derivatives of the sine is the cosine, plus, let's see, we'll do it this way, L times cosine of theta times the derivative of theta with respect to time, that's theta dot. And y dot is similarly a times omega cosine of omega t, derivative of the first term, minus L times the derivative of the cosine, which is minus the sine, therefore plus L. Then I have a theta dot again, sine of theta. So far, I hope this was not too difficult. But now that I have the velocity, I can do the square. Let's see, do I really want to do it, or just tell you what the answer is? Okay. I don't want to do it, but let's do it anyway. X dot square plus y dot square gives me the velocity square, and I multiply by 1/2 of m. Now, from x dot square, I'm going to have a square omega square sine square of omega t. From y dot, I'm going to have a square omega square cosine of omega t square. So I just take the sum of the two and write it as a square omega square. Similarly, I have L squared theta dot square cosine square plus L squared theta dot square sine square. L square theta dot square. And then I have the cross terms, the annoying ones. I have minus L A omega theta dot sine omega t cosine theta plus L A omega theta dot cosine of omega t sine theta. And for this, I will ask you to go find it in some textbook, but this is a classical sine alpha cos beta or cos alpha sine beta type of trigonometric expression. Long story short, I'm just going to tell you what the answer is. Well, it's not the answer. There is nothing wrong about the way it's written, but we can make it more compact. And I'm going to use a square bracket here now. So the first two terms are okay as they are. The last one is also okay, but don't like it too much. So let me modify it a little bit. Sorry, I'm missing some tools here. This turns out to be 2L theta dot square times A times omega times the sine of theta minus omega t. Notice that this is not the only way to write it, but that's the kinetic energy. For the potential energy, easy. U is equal to M times G times Y. I'm just going to set the potential energy equal to 0 for Y equals 0. What was the expression for Y? We still have it up here. That's going to be equal to M times G times A sine of omega t minus L cosine of theta. Okay. Looks good. I'm going to square it, even though this was close to 0 work. And then I can write the Lagrangian as t minus u. So 1/2 of m a square omega square plus L square theta dot square plus 2 L theta dot A omega sine of theta minus omega t minus mg A sine omega t minus L cosine of theta. And now we can write the equations of motion. I'm going to need the derivative of the Lagrangian with respect to theta dot, and then I'm going to take the derivative with respect to time. Let's do this derivative first. Well, theta dot only appears inside the square bracket, and I'm going to have 1/2 of m. First term does not have theta dot. So L 2L square theta dot plus 2L A omega sine of theta minus omega t. Then I take the derivative with respect to time. Now here you have to be a little careful, but let me get rid of the 2's first. Okay, so I take the time derivative of this quantity. This is a total derivative, not a partial derivative. So I'm going to have the derivative with respect to time of theta dot, which is theta double dot, L square plus L times A times omega. These are all constant. Then I have the derivative of the sine of omega t, which is the cosine, theta minus omega t. And then I have the derivative of the argument, which is going to be, let's see, how do I write it so that there is no confusion? Let me do it this way. Derivative with respect to time of theta minus omega t, which is theta dot minus omega. The other piece is the derivative of the Lagrangian with respect to theta. It's fairly easy. So the first two terms don't depend on theta explicitly. The last term does. The third term does. Oops, I lost mass here. This all multiplies and, well, we're going to be in trouble. Okay, so this gives me, and I get rid of the 2 times L times theta dot times A times omega times the cosine of theta minus omega t. And the other piece gives me minus m times g times L. Derivative of the cosine is minus the sine. So that leaves me with the correct signs. Now, I see that there is a mass everywhere, so I can divide everything by the mass. I can actually also divide by L. So let me do that. And I find that L theta double dot plus A omega times theta dot minus omega times the cosine of theta minus omega t. The first piece is equal, so I don't have to worry about an extra sign, to theta dot A times omega times the cosine of theta minus omega t minus g times, that's g not y, sine of theta. Next step, we're pretty much done. But if you notice, this term here, oh, I wanted the right pen, sorry. This term here is identical to this term here. And they have the same sign on the opposite side of the equal. So I can get rid of them. And I can, at this point, pretty much solve for theta double dot if I'm so inclined, and sure, why not? Theta double dot is equal to, what do I have left? I have this minus omega that I take to the right hand side, so it becomes plus A omega square over L times cosine of theta minus omega t minus g sine of theta. And that's the equation of motion for my system. Now, I would like to encourage you to maybe spend 10 minutes and try to do this using Newtonian mechanics and see where you get. And I encourage you to spend only 10 minutes on it and then give up, because it's going to be a nightmare. But this, from my point of view, wasn't too bad. It's all straightforward, and we found an expression for theta double dot. Now, solving this is going to be far from easy, but in principle, but we have the differential equation for theta double dot, which we may solve numerically. May also find the approximation for small theta, small oscillations, and the way we will do for the normal pendulum. Okay, so that is all. Oops. Was checking my result. There was something that looked funny. It's G over L. Notice that if I set omega equal to 0, I just get this regular pendulum, which is what I should expect. Okay, Thank you for listening, and stay tuned for the next problem. Thank you.